Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is synchronous motor starters. Our objective is to examine several types of synchronous motor starters on an introductory level. I'll try not to dive too deep into too many rabbit holes and keep this lecture brief and to the point. This lecture operates under the presumption the viewers watch the Electrically Excited Synchronous Motors lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please bring yourself up to speed and return when you are so qualified. Recalling the aforementioned lecture, I briefly mentioned the complications of starting synchronous motors. Despite the advantages of synchronous motors, notably their ability to maintain constant speed inside their operational range and their ability to operate at unity power factor given proper field current adjustment, starting a synchronous motor isn't as easy as one might initially suspect. One of the principal issues related to starting a synchronous motor is that upon closure of a full voltage starter, the stator rotating magnetic field is instantaneously established at full speed, whereas a rotor and applied load with some level of static inertia may take some time to come up to this speed. This means the stator rotating magnetic field immediately overlaps the rotor, and the rotor can't properly lock into the rotating magnetic field. This manifests itself as the motor exerting poor starting torque, drawing massive amounts of inrush and shaking. Don't believe me? Check this out. Oh, that's nasty. This is obviously not how you want to start a synchronous motor. Now realize I simultaneously energized both the stator and rotor in an unloaded condition with no counter torque. This gets so much worse with even a little bit of resistance. An apt analogy I use about starting a synchronous motor by improperly energizing the stator and the rotor at the same time is like having your buddy invite you to go water skiing only to have him pass you on the water at 60 miles per hour and toss you a rope and saying, "Let's go." It's going to rip your balls right out of your sockets if you try to accelerate that fast, and there might be better ways to reach this velocity. If you think about it, there's really only two ways to solve the mismatch between the stator and rotor acceleration. Method 1, slow the stator down, or Method 2, speed the rotor up. Method 1, slow the stator down. This method is especially apt for permanent magnet synchronous motors, since their rotor field isn't capable of being de-energized nor varied, but it also works with electrically excited synchronous motors if you're too lazy to turn the rotor field off. Given an energized rotor at rest, rather than energizing the stator with a full voltage or direct online starter, one instead uses a variable frequency drive to slowly ramp up excitation frequency on the stator so the rotor is afforded a gentle means of acceleration from 0 to 10 Hz, 10 to 20, 20 to 30, and so on up to the base frequency of 60 or whatever speed you want it to run. Similarly, a motor drive could be used to ramp down excitation frequency for a gentle stop, which leads to Method 2, speed the rotor up. There's a bunch of cunning ways to do this, and they all amount to using some trickery to accelerate a de-energized rotor until it matches, or at least gets close to synchronous speed, and then energizing the rotor field, which locks into the stator rotating magnetic field, and the motor can be put to work. One of the simplest methods of properly starting a small synchronous motor is operating them as induction motors during the starting stage, which accelerates the rotor to near synchronous speeds before turning on the exciter. This necessitates some modification of the rotor, and that in addition to the field coil reserved for synchronous operation, the rotor also needs to include a cage-like structure characteristic of an induction motor for the momentary starting phase. These are called amortisseur or damper windings. Bonus points if you can pronounce amortisseur properly, as I've yet to do so myself. You might see a timer or a rotational speed switch coordinating this transition from induction to synchronous operation. Consider a hardwire relay-based ladder logic implementation of a synchronous motor starter with amortisseur windings employing a timer executing the on-delay function. Viewers will recall an on-delay function, sometimes called a delay on energize or DOE, or slow operating or SO timer, exhibit a customizable delay between when the timer coil is energized and when the associated contacts change states. When the timer coil is energized, the associated normally closed contact remains closed, and the normally open contact remains open. Only after the predetermined delay, TD, has elapsed, does the normally closed contact open and the normally open contact close. When the timer coil is de-energized, the associated contacts immediately return to their deactivated states, i.e. the normally closed contact recloses and the normally open contact reopens. The primary circuit consists of the M stator contactor in series with the overload on the stator windings and DC-rated field contactor F on the rotor. Key to this particular application is the controlled closure of the F field contactor. We first want to close the M contactor and energize the stator with the field contactor open such that the amortisseur windings in the rotor are given a chance to accelerate the rotor to near synchronous speed. Then after a predetermined period of time, let's say 3 seconds has elapsed, close the field contactor so that the rotor locks into the stator synchronous speed. The top 3 rungs of the pilot circuit largely concern the M contactor, whereas rungs 4 and 5 concern themselves with the timer and the field contactor. Rung 1 consists of the series combination of a normally closed E-stop, a normally closed stop, a normally open start, the coil of control relay CR1, and a normally closed thermal overload. All the normally closed devices serve to de-energize CR1 in the event of an operator-initiated stop, an emergency, or a sustained overload. An operator can start the system by pressing and releasing start, which energizes the coil of CR1. When CR1 energizes, its associated contacts in rungs 2, 3, and 4 simultaneously change states. CR1 in rung 2 closes and establishes a holding circuit, allowing the operator to release start. CR1 in rung 3 closes and energizes the M primary contactor coil. The M contactor closes and the motor starts. Importantly, the motor starts without the rotor field being energized since the field contactor is open. The motor starts in induction mode, exerting a reasonable starting torque and inrush with no vibrations. The motor accelerates to just shy of synchronous speed in the no-load condition. Simultaneously, CR1 in rung 4 closes and energizes the coil of timer TR1, executing the on-delay, delay-on-energize, or slow operating function. As such, its associated contacts, notably TR1 in rung 5, remains open, and the F coil remains de-energized. This being said, the clock is running, giving the rotor time to accelerate. 3 seconds later, the timer completes the on-delay function. TR1 in rung 5 changes state and energizes the F contactor coil. The field contactor closes and energizes the rotor field, which locks into the stator rotating magnetic field, suitable for constant speed operation, characteristic of a synchronous motor. An operator wishing to stop the system reset to the starting state would press and release stop. Here's a real-time simulation of this circuit using Automation Studio. As we illustrated in the walkthrough, an operator presses and releases start to close the M contactor, establish a holding circuit, and start the timer. 3 seconds later, the timer reaches its count and closes the field contactor and energizes the rotor field. As we anticipated, the motor starts in induction mode using the amortisseur windings in the rotor, and after a predetermined delay, allowing a degree of acceleration, the field contactor closes and energizes the rotor field, which locks into the stator rotating magnetic field, suitable for constant speed operation, characteristic of a synchronous motor. Here's the system in operation once again. You note this method is pretty simple, suitable for smaller motors only, and since it's making its decision on time only, doesn't ever verify if the rotor actually has accelerated near synchronous speed before it closes the field contactor. For this reason, instead of a timer, you might see a rotational speed switch or other sensory device in charge of the field contactor, only closing it when it's really appropriate to do so. Even more robust implementations might incorporate both sensory devices and timers to not only verify if the rotor is actually at the appropriate speed, but also call it off if it's taken too long. We'll examine a more robust circuit in an upcoming application. Here's an entirely manual implementation of a synchronous motor starter using amortisseur windings. When I energize the stator field only, the cage-like amortisseur windings act like the cage of a squirrel cage induction motor, and the motor accelerates to near synchronous speed. When it's close enough, I energize the rotor field winding, and the rotor locks into the stator and starts turning at synchronous speed. Moving on. Another popular method commonly used to start a synchronous motor is to, believe it or not, use another motor or mechanical means like a gas-powered engine, a hydraulic motor, or a domestic animal to accelerate an unloaded rotor to near synchronous speed before turning on the exciter. You think I'm joking about the animals, but I'm not. This method is called a pony motor for valid historical reasons. A pony motor is essentially a small motor used to simply get the rotor turning, not to do any actual work. Consider some giant 1,000 horsepower synchronous motor with a large number of pole pairs suitable for exerting high torque at low speeds. Such a massive rotor would have obvious difficulties accelerating at synchronous speed. For this reason, a smaller induction style or a DC motor mounted on the same shaft is energized and used to get just the rotor turning. Once accelerated to near synchronous speed, the rotor field is energized, which locks into the stator rotating magnetic field. At this time, the pony motor is de-energized, and the synchronous motor can then be put to work, turning an entire dug fir into a bag of bark chips or whatever it's supposed to do. Long story short, stator and pony motor on, DC exciter off. When the rotor is close to synchronous speed, the stator stays on, but the pony motor and DC exciter perform a coordinated handoff to pony motor off and DC exciter on. DC-style pony motors can also serve as an additional capacity. As with three-phase AC machines, there are DC motors and DC generators. given an electrically excited synchronous motor necessitates DC for the rotor field, oftentimes a shaft-mounted DC motor, once it has served its initial purpose of accelerating the rotor to near synchronous speed, can be repurposed as a DC generator and supply the necessary DC field current to the synchronous motor rotor. In this capacity, the exciter circuit itself can govern when it is appropriate to energize the field or not. I feel this application needs a little explanation since most textbooks I've encountered dedicate a single diagram and a short paragraph at most describing its operation. Into the rabbit hole we go. By the time I wrap this up, we might have to rename this lecture as synchronous motor starters, synchronous motor exciters, and synchronous motor protection mechanisms. Besides the multiple functions served by this application, one of the difficulties in reviewing this circuit's construction is the range of terminology and the numerous acronyms employed. So let's conduct a brief review and introduce each component one by one rather than tackling this thing all at once. AC motors and generators are known to have stators and rotors. The stator is the stationary part and the rotor rotates. You'd think they use the same terms for DC motors and generators, but they don't. The field winding is the stationary part and the armature rotates. There's some complications for this particular application though, because the winding on the rotor of a synchronous motor is also sometimes called the field winding. Long story short, there's a stationary DC field on the DC machine and another entirely separate rotational DC field on the synchronous motor rotor. Don't mix them up. The DC generator, the combination of a field and armature, acts like a DC source, and it sends DC energy to the synchronous motor rotor field winding. If one was to draw a functional box around the DC source, I'd draw a box around the armature and the field winding of the DC generator. If one was to draw a circle around the DC load, I'd draw a circle around the rotor field winding of the synchronous motor. Tracking so far? The starting and protection circuit is in between the source and the load. We'll populate the starting and protection circuit component by component, examining each one in detail in a moment. Another difficulty in discussing this circuit is it necessitates some general knowledge of DC motors and generators. You may or may not have experience with them, but here's a summary. Different types of DC machines have different arrangements of field and armature windings. The field and armature of a separately excited DC motor are isolated from one another. The field and armature of series DC motors are in series with one another. The field and armature of shunt-wound DC motors are in parallel with one another. The field and armature of compound-wound DC motors are in series parallel with one another, and so on. This particular application makes use of a shunt-wound DC motor, which places the field and armature windings in parallel with one another. As the armature is rotated inside the stationary field winding, it generates a DC voltage. If you want to think of it this way, my earlier inclusion of both the armature and shunt field as a source was a little too hasty. The armature is technically the voltage source, and in addition to supplying the DC voltage for the synchronous motor rotor field winding, it also supplies current to its own shunt field winding, and this capacity is referred to as a self-excited shunt-wound DC generator. Oftentimes, a shunt winding branch includes a variable resistor in series with it, which kind of acts like a flow control valve for current through the field winding. By adjusting resistance in the shunt field winding branch, one steps up or down current through the field winding, thus influencing the voltage produced by the DC generator. When you actually make connection to the rotor, this is what varies the rotor field current, thus influencing pull-out torque and reactive power requirements while the synchronous motor is in operation. Speaking of connection, let's now take a look at all the stuff in the middle that makes connection. You'd think it'd be a simple DC-rated contactor, but it isn't for a very important reason. Remember when I told you that the synchronous motor rotor field winding was a load? Well, it turns out that was a little too hasty also. When a synchronous motor is first started, the rotor field winding can also act like a source, in this case AC. Think back to your understanding of Fleming's law of electromagnetic induction, which states a voltage will be induced across the terminals of a conductive coil in a changing magnetic field proportional to the rate of change of magnetism and the number of coils in the changing magnetic field. Well, check it out. That rotor field winding at rest is a conductive coil inside a changing magnetic field. Think about it. As we discussed earlier, the state of rotating magnetic field doesn't necessitate time to accelerate and is instantaneously established at synchronous speed. The motor of the stator contactor makes connection with primary three-phase AC voltage. In doing so, the rotor lagging behind the stator experiences a massive surge of induced AC voltage across the rotor field winding, which can actually damage it. For this reason, the rotor field winding includes a resistor, known as a field discharge resistor connected in parallel. Making and breaking connection to the rotor field winding and the DC exciter necessitates coordination with a field discharge resistor. This coordination is facilitated with a combined device known as a field contactor and field discharge switch F, which includes both normally open and normally closed contacts. These contacts behave a little differently than your average device and necessitate some explanation. In your average device, let's say a relay, as soon as the coil is energized, both the normally open and normally closed associated contacts simultaneously change states. Not so with the field contactor and field discharge switch, because there's a little delay allowing for a stage transition. Long story short, the rotor field winding always needs something attached to it, either the field discharge resistor or the exciter, and quite like your lazy lab partner, should never be left alone and unattended. The field contactor and field discharge switch makes connection to the DC exciter like this. Resistor only, then resistor and DC exciter, and finally DC exciter only. Breaking connection to the DC exciter is an almost identical process, only it happens in reverse. From exciter only, it goes to exciter and resistor, and then to resistor only. Note the momentary transitional handoff state for both actions. The staged make and break is necessary since it allows a current path for any induced voltage generated on the rotor coil when the magnetic field collapses. As the name implies, the field discharges into this resistor. Now that we know how the field contactor and field discharge switch work, let's examine some protection mechanisms. Oftentimes an exciter will have fuses or circuit breakers to protect the DC generator and rotor field winding from a fault condition. Simple enough. The next level of protection is known as an out-of-step relay, or OSR. The sensor mechanism for the OSR appears in series with a field discharge resistor. The OSR also appears as a normally closed contact in the control circuit. The OSR, if you want to think of it this way, kind of acts like an overload element on the rotor and protects the rotor from excessive sustained current draw. Consider a scenario in which the stator is energized and the DC rotor is lagging behind it. In this scenario, any AC voltage induced across the rotor causes current to flow through the series combination of the field discharge resistor and the OSR. The OSR keeps a running tally of how long it's experiencing current. In ordinary circumstances, the rotor eventually catches up close to the stator in a reasonable amount of time, and the field contactor and field discharge switch performs a stage handoff between the DC exciter and the field discharge resistor, and the OSR device gets a break and time to cool down. If, however, the field contactor and field discharge switch don't perform the handoff because the rotor is still lagging or out of step, hence the name, the OSR eventually says, "Give it a rest, buddy," and opens the normally closed contact in the pilot level control circuit, which opens up the M stator primary contactor and de-energizes the system. Only when the OSR normally closed contact recloses can the motor be restarted. In this capacity, the OSR limits the time it takes to synchronize the motor. When it takes too long, it calls it off. As we'll soon learn, this also works when the rotor loses synchronization and takes too long to resynchronize. The operation of the OSR is sometimes described as an overcurrent relay with time delay. So far we've discussed the DC exciter, the field discharge resistor, the field contactor and field discharge switch, exciter fuses, and the OSR. We've yet to discuss the element that has decision-making authority for the actual moment of connection, notably the field contactor and field discharge switch coil F. When the F coil is energized, the field contactor and field discharge switch do their thing and make their staged connection to the rotor. When the F coil is de-energized, the F contactor and field discharge switch again do their thing and make their stage break with the DC exciter. Key to energizing and de-energizing the F coil is a series combination of a normally open auxiliary contact associated with the M primary contactor and the normally closed contact of an interesting device known as a polarized field frequency relay, or PFFR, also known as a field application relay or polarized frequency relay. The PFFR behaves a little differently than your average relay in that it has two coils, a DC-rated coil and an AC-rated coil. The normally closed contact associated with the PFFR only changes states when both the DC and the AC coils are simultaneously energized. Given the de-energized electromechanical state, i.e. normally closed the PFFR contact, you don't want both coils of the PFFR simultaneously energized if you want this motor to run synchronously. For the F coil to be energized, the stator primary contactor needs to be closed, and the normally closed PFFR contact needs to remain closed. Long story short, the only time you should ever connect the DC exciter to the rotor field winding is when the DC exciter is working, i.e. there is DC, and the rotor speed is really close to stator speed, i.e. there is no AC. The DC coil for the PFFR is placed across the terminals of the DC exciter. This is simple enough. When the DC exciter is producing DC, the DC coil of the PFFR is energized. Makes sense. The AC coil, in contrast, is placed in parallel to a reactor or inductor, and this parallel combination is in series with the rotor field winding. Key to the PFFR AC coil operation, or for that matter the entire PFFR, is your understanding of inductive impedance. You'll no doubt recall the impedance of inductor can be calculated as 2 pi FL. The take-home point being inductive impedance is directly proportional to excitation frequency, meaning high-frequency AC results in high impedance, whereas low-frequency AC results in low impedance. This means current might find one path, i.e. the reactor or the AC coil, more preferable than another. Again, think back to the moment the stator field is instantaneously established and the rotor is lagging behind, with the field contactor open and the field discharge switch closed. The rotor experiences high-frequency induced AC voltage because there's such a tremendous difference between rotor and stator. At high frequencies, the reactor or inductor is a high impedance load, and as a result, most of the current goes through the AC coil. In this wind-up stage, when the stator primary M contactor is closed, and before the field contactor is closed, both the DC and the AC coils of the PFFR are energized. The normally closed contact associated with the PFFR contact opens and prevents the F coil from being energized. It makes sense. There's DC in the exciter, but you don't want to make connection to the rotor field winding just yet because the rotor is lagging behind the stator too far. Things change when the rotor, accelerated by other means, starts matching the stator rotating magnetic field. The differential between the rotor and stator begin to erode, and given lower frequency, the reactor presents a lower and lower impedance path, and more current travels through it and less through the AC coil. At a certain point, so much current is going through the reactor, the AC coil is de-energized, and the PFFR returns to its deactivated normally closed state. Given the M contactor is closed, and only the DC coil, the PFFR, is energized, the F coil is energized, and the field contactor and field discharge switch make the stage connection to the rotor. In addition to facilitating synchronization, the circuit also works to protect the system when the rotor is energized and loses synchronization with the stator. Anytime there's a mismatch between the rotor and stator, there's AC on the rotor, and the PFFR recognizes and responds to this undesirable scenario by facilitating a stage break with the DC exciter. If the rotor catches back up, the AC coil is de-energized and the PFFR normally closed contact recloses and reconnects the exciter. If, however, it's taken too long to resynchronize, the OSR puts up with it for a little bit, but after a while it says shut it down and opens the M primary contactor. Long story short, there's a lot going on in the circuit and a lot of things happening at once. For this reason, let's conduct a brief review. The DC exciter is a shaft-mounted DC generator. The armature is the rotating part, and the stationary shunt field winding is in parallel with it. The variable resistor in series with the shunt winding modifies the output of the DC exciter. The fuses or circuit breakers serve to protect the rotor field winding in the DC exciter. The rotor field winding is a rotating part of the synchronous motor accessible by slip rings. In synchronous operation mode, it acts like a load. If, however, the rotor lags behind the stator rotating magnetic field, the rotor experiences induced AC voltage. Additionally, if suddenly de-energized, a collapsing magnetic field in the rotor can cause a spike in voltage. For this reason, a field discharge resistor is placed in parallel to the rotor field winding. The OSR, in series with the field discharge resistor, detects presence of current. In the event of sustained current draw, the normally closed OSR contact in the pilot circuit opens and de-energizes the system. This works to prevent too lengthy of a synchronization or resynchronization event. The operation of the OSR can be summarized as an overcurrent relay with time delay. The field contactor and field discharge switch make and break connection to the rotor field winding and field discharge resistor in a staged fashion. First resistor only, then resistor and exciter, and finally exciter only. Breaking contact occurs in reversed. First exciter, then resistor and exciter, then resistor only. The state of the field contactor and field discharge switch is controlled by the F coil. The F coil is in series with a normally open M auxiliary contact and a normally closed contact associated with PFFR, the Polarized Field Frequency Relay. The PFFR is a little weird because it has two coils, and both coils need to be simultaneously energized for this normally closed contact to change states. The DC coil is in parallel to the DC exciter. The AC coil, in contrast, is in parallel to a reactor or inductor, and this parallel combination is in series with a rotor field winding. During the acceleration phase, there's a large difference between the rotor and stator field, and there's AC on the rotor. This opens the normally closed PFFR contact, preventing the F coil from being energized. If, however, the rotor reaches within 90% of stator speed, the low impedance path around the AC PFFR coil de-energizes it, and the normally closed PFFR contact recloses and allows the F coil to be energized and make the stage connection to the rotor field winding. Lastly, I should mention you might run across an additional protection mechanism in series of the rotor field winding known as a loss of excitation, or LOE relay. Whereas the OSR is an overcurrent relay with time delay that is sensitive to induced AC, the loss of excitation relay, or LOE, is an undercurrent relay with time delay sensitive to exciter-provided DC. As the name implies, if DC excitation current ever drops too low for too long, the LOE says give it up and de-energizes the system. Depending on application, you might see an LOE relay pilot contact in the holding circuit, the pilot level circuit, to break connection. All right, that's about it. Since we kind of veered away from our discussion of solely synchronous motor starters and started touching on exciters, I admit I was mighty tempted to dive right into a discussion of brushless exciters. Given brushless exciters operate using power electronics devices like diodes and rectifiers we've yet to discuss in detail, I'll save that for another exciting lecture. Until then, that's all I've got for you. In conclusion, this lecture discussed several different methods of starting synchronous motors, including motor drives, amortisseur or damper windings, and pony motors. Additionally, we discussed some of the coordination and protection mechanisms inside a DC exciter circuit and examined the operation of components like the field discharge resistor, the field contactor and field discharge switch, the polarized field frequency relay, the out-of-step relay, and the loss of excitation relay. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.